Theodolite. Most importantly is to define the theodolite at the start. It is an instrument that is used to determine horizontal and vertical angles through horizontal and vertical circle readings. So the theodolite does not measure angles. It measures horizontal and vertical circle reading. قراءات على الدايرة الأفقية والدايرة الرأسية، ومنها نقدر نحصل على الزوايا. دي أهم حاجة في بداية التعريف التدريجي. Different types of theodolite. Theodolite will differ according to the method of reading. على حسب طريقة أخذ القراية. Vernier theodolite, theodolite الورانية, is the very old and obsolete theodolite, but we can see here the vertical circle and the horizontal circle. You can see them easily. الدايرة الرأسية اللي هيتاخد عليها القرايات الرأسية أو قرايات الدايرة الرأسية، والدايرة الأفقية اللي هيتاخد عليها قرايات الدايرة الأفقية. Afterwards, they moved to optical theodolite. We covered the horizontal and vertical circles made of glass and hidden inside the instrument, and you can get the readings through a reading telescope. Through a reading telescope عن طريق منظار للقرايات. But the optical theodolite أو التدوليت الضوئي is less used now because it requires a source of light. محتاج مصدر إضاءة عشان نقدر نشوف أكتر أو نقدر نشوف قرايات الدائرة الأفقية والرأسية. Otherwise you will not see anything through the reading telescope. Most common, most popular is the digital theodolite. Theodolite الديجيتال أو الإلكتروني. It is the easiest and most common theodolite. Of course, it is the most expensive due to the more modern technology. The readings of the horizontal and vertical circle are transformed on screen. So you get HCR, horizontal circle reading, or VCR, vertical circle readings, directly on screen. So in the vernier theodolite, you take the readings by yourself from the horizontal and vertical circles. In the optical theodolite, you take the readings through the reading telescope, while in the digital theodolite, you take the readings directly from screen. The different components of the theodolites. First, the leveling screws, مسامير التسوية, in order to level the horizontality of the theodolite. The theodolite has two types of motion, horizontal and vertical motion. Horizontal motion, we have the clamp screw and the slow motion screw, مسامير للحركة الأفقية البطيئة والحركة الأفقية السريعة. For the vertical motion, we have also a clamp screw and a slow motion screw, مسامير الحركة الرأسية السريعة والبطيئة. Optical plummet, منظار التسامد. منظار التسامد in order to see the point that you're occupying، عشان نقدر نسامد أو نشوف النقطة اللي احنا واقفين عليها. And this is done through a 45-degree prism. So you look inside the optical plummet and you see the ground. The theodolite has a circular and a plate level tube. A plate level tube ميزان طولي وميزان دائري in order to fix the horizontality. So these tubes or these circular and plate level as an indicator for the horizontality of the theodolite. Mirror and micrometer to take the readings in the optical theodolite. But in the case of the digital theodolite, then we don't have a micrometer, we don't have a reading, we don't have a reading telescope, because digitally it is on screen. Eyepiece, the eyepiece العدسة العينية, and the eyepiece screw اللي بتوضح صورة حامل الشعرات اللي هنتكلم عليه بعد شوية. Focusing knob. The focusing knob is used to clear the vision of the target, or to focus on the target. objective lens العدسة الشيئية اللي بيخرج منها الشعاع بتاع عيني. horizontal circle, vertical circle الدايرة الأفقية والدايرة الرأسية. Alidade is the upper part of the theodolite without the base, without the screws, without the horizontal circle. So the whole instrument is called theodolite, but the upper part only is called the alidade أو بالعربي بيسموه الأليداد. From this figure, you can see easily how in the optical theodolite we have a mirror. Mirror can focus the sun radiation or sunlight, then it transform it inside the theodolite, which will enlight the vertical circle, and then through a 45-degree prism you can also light up the horizontal circle. Also it's a cross section in the theodolite, makes you see this is the reading telescope, because this is an optical theodolite. This is the telescope itself, the eyepiece, the objective lens, the focusing lens, mirror, vertical circle, horizontal circle, the screws that we use to deal with the theodolite. By looking at the telescope and taking a cross section in the telescope, you can see the eyepiece, the objective lens, the crosshair, حامل الشعرات or the reticule, and the focusing lens. It's the same for any surveying device. The telescope for any surveying device, whether it's a theodolite or it's a level, it's the same. The crosshair is required. This is a cross section in the crosshair. Vertical hair, horizontal hair, شعرة رأسية, شعرة أفقية, two stadia hairs. What you will do, you're going to point out using the crosshair to target points using the cross intersection of the vertical hair and the crosshair. The focusing lens is controlled by a focusing knob in order to move the focusing lens forward and backward until the image of the target that you want coincides with the plane of the crosshair. تطابق صورة الهدف مع حامل الشعرات. Concept of measuring horizontal angle. الفكرة الرئيسية وراء قياس الزاوية الأفقية. After fixing horizontality and plummeting، بعد ضبط الأفقية والتسامد، عايزين ناخد قرايات دايرة أفقية ونقدر نعين الزاوية الأفقية. بعد ما نعمل الأفقية والتسامد هنوجه على نقطة A وناخد ال HCR horizontal circle reading target point A or direction to point A. This direction is projected on the horizontal plane formed by the theodolite, and then rotate clockwise. Target point C, this direction is projected on the horizontal plane formed by the theodolite, and the angle measured between these two projected directions is the angle that we want, which we call it ABC. The angle is measured from left to right clockwise direction, from left to right clockwise direction. So it is the angle between the projection of two lines on the horizontal plane passing by the theodolite في اتجاه عقارب الساعة. Any horizontal angle could range from 0 up until 360 degrees. If sometimes happens that theta is negative value or the horizontal angle is a negative value, then we add 360 degrees because 360 does not affect the angle. It has to be mentioned here that in this case the horizontal circle is fixed, it doesn't rotate, while the one rotating with the alidade or the telescope is the pointer. The pointer المؤشر اللي هياخد القراية على الدايرة الأفقية. فإن this case only the pointer rotates with the alidade while the horizontal circle is fixed. For any horizontal angle, it is the HCR, horizontal circle reading of the last point, minus or subtracted from it horizontal circle reading of the initial or first point, and this again proves that we don't measure the horizontal angle using the theodolite. We measure horizontal circle readings, and then through these readings we can determine the horizontal angles. Regarding vertical angle, also of course we fix the horizontality and the plummeting الأفقية والتسامح, but in this case the theodolite does not measure the vertical angle. The vertical angle is the angle between the line joining the theodolite and the target, which we call it the line of sight أو خط النظر, and the horizontal plane passing by the theodolite. But the theodolite does not measure the vertical angle, الزاوية الرأسية. It measures the zenith angle, زاوية السمت اللي مع الرأسي. In order to calculate the vertical angle from the zenith angle, so V equals 90 minus Z. If it is upwards, then the vertical angle is positive. We call it elevation angle, زاوية ارتفاع. If it's negative, then it's downwards, and we call it depression angle, زاوية انخفاض. Important point should be highlighted here, that the height of the point or the height of the theodolite itself does not affect the horizontal angle. Why? Because everything is projected on the horizontal plane. On the contrary, in the case of the vertical angle, the height of the theodolite or the height of point will surely affect the value of the vertical angle itself. To understand more the idea about the vertical angle, and to see how the theodolite really actually measures the vertical circle readings and obtain the vertical angle, let's first introduce two faces of the theodolite. نتعرف على وضعين للجهاز. Face left وضع متيسر, face right وضع متيمن. Face left, if the vertical circle is to the left of the observer. لو الدايرة الرأسية على شمالي يبقى أنا في وضع متيسر. Face right, vertical circle on my right. لو الدايرة الرأسية على يميني يبقى أنا في وضع متيمن. Let's have a look on what actually happens when we measure a vertical angle using theodolite. This is a cross section in the vertical circle. This is the vertical circle, this is the telescope, this is the index. It's like the pointer in the horizontal circle, but we call it an index to differentiate between the horizontal and the vertical. If the telescope is horizontal in case of face left, you will find that the VCR in face left equals to 90 degrees. This index is usually fixed from one part and hanging freely horizontal as much as possible from the other part. So this is the case if the telescope is horizontal and the VCR equals to 90 degrees. We want to measure a vertical angle to point A. So we're going to target point A. In this case, the telescope will rotate with the vertical circle while the index is fixed. This is completely the opposite to what happens in the horizontal circle. In the horizontal circle is fixed and the pointer rotates with the alidade. In the vertical movement, the telescope rotates with the vertical circle and the index remain as it is. The vertical circle reading in face left after you point it towards point A will be somewhere from 0 to 90 degrees. So it will be a value smaller than 90 degrees. So if the telescope was horizontal, it was 90 degrees. When you moved, you got a VCR less than 90 degrees. So what's the value of the vertical angle? The vertical angle will equals to 90 degrees minus vertical circle reading in face left. Of course, if the VCR is smaller than 90 degrees, then the vertical angle will be positive, as in our case here. While if the VCR is greater than 90 degrees, then the vertical angle is negative and you're pointing downwards. Let's rotate from face left to face right. How do we rotate from face left to face right? If you want to get the vertical circle from your left to your right, then you will have to rotate the alidade 180 degrees, then rotate the telescope 180 degrees. So the alidade will rotate 180 and the telescope will rotate 180 degrees. When you rotate the alidade 180 degrees, 180 and 0 will be in the same position, but 90 and 270 and the index will shift their positions. Then when you're going to rotate the telescope 180 degrees, all the vertical circle will rotate as well. So 90 and 270 will return to its initial position, while 0 and 180 will change position. So you will end up with this figure as illustrated. 90 and 270 remained the same, 0 and 180 changed position, and the index as well changed their position. We want to target the same point A. You can see that in the case of face right, if the telescope is horizontal, then the VCR equals to 270 degrees. I'm going to target the same point A. What will happen? The telescope will rotate. The telescope will rotate, so the vertical circle will rotate as well. And you will get a VCR at point A somewhere greater than 270 degrees. So what's the vertical angle? The vertical angle will be this value. It's the VCR minus 270. Same thing, if the VCR is greater than 270 degrees, then the vertical angle will be positive. If the vertical circle reading is smaller than 270 degrees, then the vertical angle will be negative. The vertical angle that you want from face left or from face right could be either 90 minus the VCR in face left or VCR minus 270 in face right. And since it is the same point, then the vertical angle from face left should equal exactly the vertical angle from face right. After speaking about the horizontal circle and the vertical circle and how do we measure horizontal angle and how we measure vertical angle, there is a very famous error in the theodolite called the index error, خطأ الاستدلال. What happens? In the horizontal circle, the pointer is resting on the horizontal circle, and we already take the difference between the horizontal circle reading. So if there is an error in one direction, it will be removed when we subtract the other direction. But in case of the vertical circle, the index is fixed from one end. So due to the usage of the theodolite, the continuous usage of the theodolite, or due to any facing of any shock movements أو الجهاز اتخبط أو أي حاجة, or of course due to gravity force الجاذبية, the index could tilt a bit downwards, usually downwards. طبعا ممكن تحصل يبقى في it will tilt upwards in some cases لو اتخبط بصورة معينة. What we need to know, because we can't see the instrument from the inside, we want to know if there exists an error in the theodolite when measuring the vertical angle, or if there exists what we call the index error. So I'm assuming here that the index is tilted downwards by a value equals to delta. This value, this angle, we call it the index error أو خطأ الاستدلال. I'm assuming it's tilted downwards because usually due to gravity the index will tilt downwards. How we're going to discover it, we're going to mention it later. Let's assume that we know the value of the index error delta, and we're going to target the same point A. So I targeted the same point A. The vertical angle from the previous slides equals 90 minus VCR. But 90 minus VCR will get you this whole angle. I want the correct proper angle only. So it will be 90 minus VCR and then subtract the value of the index error. So it's 90 minus VCR minus delta. In the other case, when you rotate the alidade 180 degrees and you rotate the vertical circle or the telescope 180 degrees, you will end up with this figure, the same as before, but the index is tilted still downwards, but in the other direction. And I'm going to point to the same point A, our target, the same point A. In this case, VCR minus 270, as from the previous slide, will not equal the vertical angle or the proper vertical angle that we need. So VCR minus 270, we need to add to it the value of the index error delta in order to be equal to the vertical angle. So the correct vertical angle will be VCR minus 270 plus delta. This is the case if we have an index error and we know its value. How can we substitute with this error and still get the vertical angle or the correct vertical angle, whether from left or from right? Fortunately, the vertical angle from face left should equal the vertical angle from face right, and since we're pointing to the same point, I'm going to equalize vertical angle left to vertical angle right, since it's the same point. So 90 minus VCR left minus delta equal VCR right minus 270 plus delta. Delta will go to the other side, it will be 2 delta. 270 will go added to 90. VCR right will go with a negative sign on the other side, ending up with 2 delta equals 270 plus 90 minus VCR left minus VCR right. 270 plus 90 equals 360 minus common factor, so it's VCR plus VCR divided by 2, ending up with the famous equation for the index error. الناتج أو المعادلة الرياضية لخطأ الاستدلال equals 360 degrees minus summation of VCR left plus VCR right over 2. How to calculate the index error and how to obtain the vertical angle correct if we have an index error. The problem still remaining is how to discover if we have an index error or not. Simply this can be answered through the equation. When is the index error on when is delta equals to 0? If VCR left plus VCR right equal 360 degrees, then this is what you need to do in order to know if there is an index error in the theodolite or not. Fix the horizontality, fix the plummeting, اظبط الأفقية والتسامح, target to any point, target to any point. If the vertical circle reading from face left plus the vertical circle reading from face right equals to 360 degrees, then index error equals to 0. If not, then add them up together, subtract it from 360, divided by 2, you'll end up with the index error. The index error itself could be a negative value. What does it mean if the index error became a negative value? It means that it's contradicting the assumption you made that the index is pointing downwards. So if you got it as a negative value, then the index is pointing upwards. But as I said, the usual case is when the index error is tilted downwards. Also, the determination of the index error is usually done during the calibration process في معايرة الجهاز, because when you want to get the index error of the instrument or of the theodolite, you don't do it once, you do it more than one time, and they should yield the same value. But if not, and they are close to each other, then you can average them and use one value. What's important is that you use one value for the index error for all points, because you have to remember that it's the same theodolite. How to measure horizontal and vertical angles? This is the procedure of how do we measure any angle or any number of angles using the theodolite. The proper procedure that we go through. First, you finalize the plummeting and the leveling, or the plummeting and the horizontality over a certain point A. هنظبط الأفقية والتسامح على نقطة A. Target towards point B, say in face left, and take whatever available reading that you have. So you'll measure the HCR and VCR at point B, and they are easily demonstrated on the screen in the case of the digital theodolite. Then rotate clockwise direction to point C in the same face, and get the horizontal circle reading in face left for point C, and the vertical circle reading in face left for point C, and so on for all target points. Say you have points D, E, F, and G. Finalize all directions in one face in clockwise direction. At the last point, after you finished and you got the readings that you want, so at the last cited direction, turn from face left to face right. How? By rotating the alidade 180 degrees and rotating the telescope 180 degrees. Start again, taking the readings for point C, or for the last cited direction, HCR and VCR, and then go backwards in an anti-clockwise direction to all points until you return back to the first direction. Take the horizontal circle reading in face right for point B. Then you will finalize all directions in one face clockwise, and then the other direction in the other face. Why are we doing so and not taking face left and face right at the same point? Because if we have a creep error, خطأ الزحف، الدائرة الأفقية لو بتتحرك معايا وأنا بتحرك في clockwise direction في face left, it will turn out and get back to its initial position, or to 90% of its initial position when we return in the anti-clockwise direction. So this is the procedure we work. We finalize all points in one face and then the other points in the other face, ending up with 2 readings for the HCR and 2 readings for the VCR for each point. In the case of the HCR, we'll calculate the mean HCR. We have an HCR from face left and HCR from face right. We'll calculate the mean from face left and face right for all directions. Calculate the horizontal angles from the mean HCR between different points, as will be mentioned later. Calculate the corrected horizontal angles if possible, as we're going to see also later. Calculate the index error. If we got the VCR left and right for any point, you can calculate the index error, and calculate the vertical angles taking into consideration the index error that you just calculated. In theodolite, we have 2 methods of measurements, or 2 modes of measurement: the single angle method and the closing horizon method. We'll start with the single angle measurement. Say we have only 2 directions, then we'll occupy point A, target at point B, take the measurements in the same sequence, HCR, VCR, face left and face left, then go to point C, take the HCR and VCR face left and face left, and then turn at point C from face left to face right and go back in the other direction, or the if you went clockwise in face left, then anti-clockwise in face right. And if you have more than 2 directions, for example 3 or 4 directions, then the sequence will be the same. Take all measurements in face left, then face right, or start with face right and then face left. But as we mentioned earlier, we finish one face for all points and then the other face in the other direction. Why do we have gaps? Maybe you don't want to determine the vertical circle reading or the vertical angle at point D. Why we don't have face right at point C? Because you already calculated the index error from VCR left and right, and no need to calculate it once more, because it should be the same. This is for the single angle. Now for the closing horizon. The closing horizon technique or closing horizon measurements بنسميها طريقة قفل الأفق. In order to see how do we work with the closing horizon method, let's apply it directly on a solved example. The main difference here in the closing horizon measurement is that we start from a point, take all measurements, and then end at the same point. So we rotate a 360 rotation. So we end at the starting point. This will make availability for checks, as we're going to see, and thus this will produce more accurate and more reliable measurements. Solved example. Given the following tabulated theodolite readings, calculate the corrected horizontal angles BAC and CAB. So whenever there is a closing horizon, there will be corrections because we measured the angle internally and externally. If it's single angle, then we won't have any corrections for the angles. Index error of the theodolite, corrected vertical angles to B and C. Why corrected vertical angles? Because you're going to calculate the index error. Again, why do we have gaps here? Because index error is already calculated at point B, so no need to calculate at point C. Why do we have gaps here? Because the vertical angle at point B is the same whether you get it from the start or the end. Important difference between HCR in face left and face right, that usually the difference is 180 degrees or almost 180 degrees. Theoretically, it should be exactly 180 degrees according to the rotation from face left to face right. You turn the alidade 180 degrees, so this transforms the horizontal circle reading from face left to face right by 180 degrees, because the rotation of the telescope won't affect the HCR at all. So common knowledge, the horizontal circle reading in face left and face right at the same point should equals 180 degrees. If not, and there is some differences as we can see in the seconds here, this is due to human error. We'll solve the horizontal part in a table, followed by the vertical part. This is the table. I just took the horizontal part. Remember that the sequence of measurements was in this order. You occupied point A, say we started in face left, then you targeted point B, you took the face left, then C, then B, and then you changed from face left to face right at point B and returned anti-clockwise until you ended up at point B once again. We need to calculate, we have HCR in face left and face right, so we need to calculate one value for the HCR. We're going to calculate the mean value of the HCR or mean HCR. We're getting the mean for the error due to human errors or due to instrumental errors or whatever. So the difference between 174 and 354 is not an error. The difference between them should equal 180 degrees. Minutes is the same, seconds are different due to human error after he pointed out to all these points and returned back again. So we're going to choose either the angles of the face left and face right. Say we're going to choose 174 degrees. So the mean will be 174. Minutes 13 and 13, 13. And we'll get the mean of 2 and 42. So 2 plus 42 equals 44, divided by 2 equals 22. Or 42 minus 2 equals 40, divided by 2 equals 20. You either add it to the small value, 2 plus 20, or you subtract it from the large value, 42 minus 20. For both, you will end up with 174 degrees, 13 minutes, 22 seconds. Remember that why 174 degrees? You could choose 354, but if you choose 354, then you have to choose the degrees in face right for all points. If you choose the degrees for face left for point B, then you have to continue the degrees for other points as well. For point C, 12,192, of course, we're going to choose 12 degrees. This is the mean value. 45, 49, 46, 25. There is a difference in the minutes as well. Remember that 1 degree equals 60 minutes and 1 minute equals 60 seconds. So we want to get a mid value between 45, 49 and 46, 25. Between 45, 49 and 46, 25, from 45 to 49 to 4600, there is 11 seconds and 25 seconds. So we have in total 36 seconds. Divided by 2 equals 18 seconds. 18 seconds, I will add them up to the smaller value. So 18, 11 of them I will reach to 4600. The remaining of 18 after 11 will be 7. So the end result will be 12 degrees, 46 minutes and 7 seconds. Or you can get it by subtracting 25 seconds, subtracting from it 18, you will end with 7 seconds as well. So the mean HCR for point C is 12 degrees, 46 minutes, 07 seconds. For point B, after you rotated 360 degrees, after you closed the horizon, it will be, of course, 174 degrees. Minutes is the same, so 13 minutes, and the mid value of 30 and 58, easily 30 plus 58 equal 88, divided by 2 equals 44. Mean HCR at point B. Let's calculate the horizontal angle. The horizontal angle BAC equals the horizontal circle reading at the final point, which is C, minus the horizontal circle reading at the initial point, which is B. So 1246.07 minus 174.13.22 equals 198.32.45. From where did we get this value? Because actually when we subtracted the HCR of C minus HCR of B, we ended up with a negative value. We don't have a negative value for the horizontal angle, so we added 360 degrees and the end product was 198.32.45. The other angle CAB equal HCR of B minus HCR of C, so 174.13.44 minus 12.46.07 equals to 161 degrees 27.37. The summation of angle BAC plus angle CAB should equals to 360 degrees, two angles at the same point, the internal and the external angle. So the summation should be equal 360 degrees. Let's check. If the summation equals 360 degrees, okay, fine, we have no problem, we have no error. The corrected horizontal angle will be the horizontal angle themselves. But if not, and I will add 198.32.45 plus 161.27.37, this will give 360 degrees, 0.22 seconds. We have an error of 22 seconds. What do we do with this error? We're going to distribute this error over the number of angles. Simply, we have two angles, so the error is 22 seconds. Accordingly, each angle will take 11 seconds of this error added or subtracted. Of course, it's going to be subtracted because the summation was greater than 360 degrees. Again, how to calculate the error mathematically? The error equal the summation minus 360 over 2 equals 11 seconds. Remember that 2 is not like the one in the index error. 2 here, it means that we have two directions, that we have two angles. If we've got B, C, D, B, then this number will be 3, because in this case you will have 3 angles. This is a very important remark. We calculated the horizontal closing error. Each angle will be subtracted by a value of 11 seconds. So 198.32.45 minus 11 seconds, and remember to write it 0 degrees, 0 minutes, 11 seconds, or on the calculator 0 dots, 0 dots, 11 dots. So if you subtracted only 11, the calculator will understand that this is 11 degrees. So remember the degrees and minutes and seconds should be distinguished properly. Corrected angle or corrected horizontal angle BAC equals to the value minus the error that we obtain, or the horizontal closing error. The final angle will be 198.32.34. Of course, it has been decreased by 11 seconds because, as we said before, the summation was greater than 360 degrees. The other angle, CAB, equal 161.27.37 minus the same value, ending up with 161.27.26. And make sure to sum up both angles after corrections and check that the summation equal 360 degrees. By this step, you now calculated the corrected horizontal angle for BAC and CAB. Now, regarding the vertical angle, we have the vertical circle reading in face left and face right for point B. We'll add them up together. If equal 360 degrees, then we don't have an index error. But the summation equals 360.0038 seconds. Then we have an index error. Index error equal 360 minus the summation of both VCR divided by 2 equals negative 19 seconds. Negative 19, negative means it's contradicting to the assumption. It's not downwards, it's upwards. It doesn't matter. We're going to substitute by the value as it is. The vertical angle at point B equals, from the common equation that we mentioned earlier, 90 minus VCR left minus delta, 90 minus 88.44.33 minus delta, which has been a negative value. Then both negative values will turn out to be positive, equal 1 degree 15 minutes 46 seconds. And if you calculated the same angle at B from face right, it should yield the same results. لو حسبنا الزاوية من الوضع المتيمن أو الوضع المتيسر، المفروض يطلع الإجابتين حاجة واحدة. 1 degree 15 minutes 46 seconds, then this is an elevation angle, زاوية ارتفاع. For point C, 90 minus VCR minus delta, we only have the VCR face left for point C, so 90 minus 91.37.19 minus the index error, we end up with negative 1 degree 37.00, so it's a negative value, so it's a depression angle أو زاوية انخفاض. A very important note, we also mentioned it before, if I gave you, or if available, the VCR in left and right for more than 1 point, then you will calculate the index error at each point. Luckily, they should be equal to each other. If not, then calculate the mean index error and use this mean index error for all points. Do not use a different index error for each point, because it is the same theodolite with the same index error, which should be only one value. Thank you.